Nylon threads pinned through metal conductors can demonstrate the electric field nicely. For example, here I have these red nylon threads pinned through this brass metal capacitor. When I charge it up, you can see the threads jutting out and pointing toward the negative grounded side. Here we learned that the electric fields are perpendicular to the surface of a conductor and point from positives to negative. Now I have a copper mesh version. You can see that the electric field is higher near the round edges and weaker where it's flat. Furthermore, if you close the circle, the electric field is zero inside. You can try to build one yourself out of aluminum foil and string, but the store-bought ones usually work better. The string must hang under its own weight or it won't work at all. If you're unable to build or buy one of these apparatus, you can get a reasonable imitation from some charged wool or cotton. This is wool from a sheep. Bah! Take the wool and charge it up. The wool hops back and forth between the two charged plates. Its acceleration is along the electric field if you neglect gravity. And like I said, cotton works fairly well too. And so does animal fur. This is dog fur from a groomer, but you can use cat fur too if you can get it. When you look closely, you recognize that the fur is standing up perpendicular to the sides, like a good electric field demonstration. Perhaps the most direct way to observe the effects of the electric field is with a cathode ray tube, particularly one with a capacitor plate built in. Power your tube with a high voltage source. I'm using the guts of an old plasma globe. Then, deflect the ray by placing another voltage source across the capacitor. This one must be DC. Note that the electrons are deflected upward in the opposite direction of the electric field. You can even verify their velocity. If you want to do this absolutely safely, you can power your CRT with a plasma globe in a dark room. Now you can deflect the beam with just the polarization of your own body, or a lower voltage of about 20 volts. This works because the electrons are now going much slower. You can vividly trace the flow of ions in an electric field with some potassium permanganate crystals that you borrow from your chemistry teacher. Inserting two electrodes and putting them to a high voltage generates these beautiful purple lines. You can even preserve the pattern if you press it in between two pieces of paper. Prepare a less than 1% saltwater solution by mass and dampen some coffee filters in it. Then place them on a plastic insulator and put high voltage electrodes on it. Turn it on and set it to about 220 volts. You should get a few milliamps. Now you're ready to dust on the crystals and enjoy the results. Now this can be a very dangerous setup. If your hand goes across the wires or even in the salt water, you could get a burn or a very bad shock. It's best not to move any of the equipment when the power's on. And be sure to warn your students. It's probably better to do this as a demonstration than a lab. The pointy end of a charged conductor has a higher electric field because of a higher density of surface charge. As a result, the air near that point, which gets charged by it, is blown away by the local electric field and the other similarly charged air molecules nearby. It is not the flame being blown by the electric field, but rather the electric field which accelerates the charged air, and that air, in turn, pushes on the flame. The electric wind can also be used as a propellant. This vane will spin away from the direction of the electrified air, By Newton's third law, the point pushes on the air, so the air pushes on the point, causing it to rotate. There are many other tricks that can be used to demonstrate the ideas of the electric field. For example, here I have a can full of styrofoam chips that should easily be deflected by the high electric field near the Van de Graaff generator. Except that the can acts as a Faraday cage. There is little to no charge and no electric field inside. Lastly, there are also simulations. These ones are from the University of Colorado. They do a good job at familiarizing students and teachers of the rules, units, and effects of theoretical electric fields. They're great, but be careful. Students will sometimes mistake this for the real physics. Always bring them back to experimental reality. Always remind them that physics is in the real world.